Hello, I'm Cade Sarkin,
I'm Vaughn Richard.
I'm Anish Patel.
and we're going to be talking about supercapacitors again. So I'm going to be explaining the drawing first. So as you can see, there's three sources of fire: a lighter, a log, and a torch. And each of these has a symbol beside it. This one has a lightning bolt, this one has a snail, and this one has a balance in between the two. So the lightning bolt represents for the lighter that this is the quickest time to light, so it's the quickest power output. And then the snail for the log shows that this takes the longest time to light, so it's the slowest power output. And then the balance in between the two on the torch showed this takes time in between both of these, so it's medium power output between the two. And then also on the torch, log, and lighter, there are timers on them, which these are representing the energy or time it takes for them to burn out. So the torch has the shortest time, the lighter has the shortest timer, so it has the least amount of energy supply. And then the log has the longest timer, so it's the most amount of energy supply. And the torch has the middle one, so it's in between those two. And then on the bottom, you can see that there's the stencil, and it is actually being or the nozzle, but it's actually being shortened up from the lighter, so it's having less distance. And then gas is being added below it, so it is having more power supply or energy supply, and then that is making it have more surface area but less distance, giving it more power output and more energy.
All right, I'm going to be going over the experiment, but before that, I'll go over some background information. Keyword is energy, and that's like the potential that a certain material has. And another one is power. That's how fast that the energy can be moved through an object or a material. So these three things represent three different devices that we learned about. One of those is a capacitor, and it has a lot of power, but not a lot of energy. That means it can really like flow energy through it, but it can't really store it. Another one is the supercapacitor. It's sort of like a mix between the battery and the capacitor. So it has like medium power and medium energy. And then there's the battery, and it has a lot of energy, but it can't really get that flowing fast. And the actual experiment that we did is we made a supercapacitor by taking these carbon like dough squares and using citric acid as an electrolyte to store energy and then discharge it.
Okay, so I'm going to talk about like what each of these objects represent when we're talking about like the experiment. So first we have the lighter in the top left. So based on the timer, how it shows that it's the shortest amount of time that it can actually stay on, and based on the lightning bolt, we can see that this is actually the capacitor because it has the least amount of power out of all of these. The most amount of power out of all of these, but has the least amount of energy stored. Because when you're using a lighter, you can really quickly turn it on, but the flame doesn't really stay that long on when you have it on. And when you close it, you need to reignite it and recharge it, so to say, kind of whenever you use it. Next, when we go on to the log, we see that it has the most amount of energy actually stored in it, but based on the snail, we see it takes the most amount of time and the effort to actually light. So we can see that that's basically the battery, because the battery has a lot of energy, but the power output isn't as strong as, say, the lighter or the torch. And then the torch represents a supercapacitor because it's in the medium between the two, which shows that it has a medium amount of power and a medium amount of energy overall. And then when we go down to here, in relation to the experiment, we saw that when you decrease the amount of distance between the plates, how we did the experiment specifically, we decreased the amount of space between the various carbon clay like dough material that we had. We decreased that space by pushing down on them to ultimately increase the amount of energy that they could actually discharge. And ultimately this was seen when we would plug it into this circuit board that had a light, and whenever we would actually turn on the supercapacitor, the light would flicker on. The more we pushed down on it and the more the distance was actually decreased, the more the light actually showed up. And another way that we actually made this capacitor a supercapacitor was by increasing surface area, which is through this oil tank that was trying to show by the artist, whoever made this picture. So when you increase the surface area, how we did that in the experiment is by flattening out these the carbon clay pieces. We flattened them out onto the different steel plates, and ultimately that allowed for more energy to be actually be used and more discharge to see the light actually turn on. So, any questions?
So the audience is also an expert in supercapacitors. Parents, any questions about the experiment or the drawing? Yes.
I think you're correct in your interpretations, but I'm just interested into thinking about the last picture at the very bottom. So that seems to have a lot of power and a lot of energy. What source of, what energy source do we have today that can provide a lot of power and a lot of energy?
All right, so the question is, what energy source do we have today that can provide a lot of power and a lot of energy? And the answer to that is fossil fuels. And we're trying to move away from those because those produce a lot of CO2, which can be harmful for the environment. So we're trying to move towards more supercapacitors.
So do you think the propane tank is supposed to show fossil fuels or just energy in general?
I think that it was believed to show just an increase in surface area, an increase in energy in general instead of fossil fuels, but it definitely seems like that's what is also putting it out there as that's that's where we get the most energy.
Okay. So you saw how fossil fuels compared to capacitors, supercapacitors, and batteries based off of what chart that they showed you. Do you remember what it was?
It was energy and power.
Mm-hmm. Do you remember the name of it by chance?
Like Rones or something like that?
Close. It was the Ragone plot.
Ragone.
So yeah, very close. So the fossil fuels and combustion was on there. Another thing that was on there was what? Do you remember?
There was a fuel cell.
A fuel cell as well. So what's the difference between the fuel cell and the fossil fuels and the battery, the capacitor, and the supercapacitor?
In terms of energy and power?
In terms of like what they are.
I think like batteries and capacitors and supercapacitors are all like forms of like storing energy, while fossil fuels is like you burn it and you like release the energy and you just obtain it and extract it from there.
Good, exactly. So the other ones that you guys actually were comparing here are all energy storage, whereas fossil fuels and fuel cells, even though they are on the plot because they do produce energy, are actually generating the energy, not just storing it and then releasing it to you. Another question I have is, so you mentioned reducing distance. So what exactly, you're reducing the distance between what and what exactly? Can you clarify that?
In this drawing?
No, in the actual experiment.
Okay. Was it between?
Yeah, like the different carbon like electrodes, and if there's a higher distance, there's more resistance, which means you get less volts. So.
And then, so what is actually like moving then within your, or what is the thing that's actually kind of helping to charge and discharge? So you have the carbon, and then what else?
The electrolytes.
Citric acid, electrolytes.
The electrolyte, right? So it's also that distance that's really critical. So it's not, so the carbon provides the high surface area, but the actual distance that's really important is the distance between the electrolyte and the carbon. So is there a lot of distance between them?
No.
Not really, right? Whereas in a parallel plate capacitor, the distance is what?
Pretty big.
Is the distance between?
We put like paper towels and like other.
And I'm not talking about the experiment. I just mean like in a general parallel plate capacitor. What is the distance that we're?
A lot bigger.
The distance between the
positive and negative charges.
the plates, right?
Yeah.
So in the case of a supercapacitor, the distance is a lot smaller, right? Because you don't have the two plates. They're just like right next to each other. Any other questions? Can the artistic team behind this drawing, I think some of you guys at least are still here. I know one of your compatriots had to catch a flight, but Did they miss anything that you guys were trying to portray?
No, they pretty much got everything.
They got it all?
Yeah.
All right. Cool. Thank you, guys.